You got sound? Okay. Okay, we were talking about stainless steels. We talked about steels the other day, but I forgot to hand out this handout, so you can pass this around. I was using some of the overheads from it. And so far as stainless steel goes, I started using this handout yesterday, which is the genealogy of stainless steels, and that's what I'm going to finish up on stainless steels today, is the genealogy. I also handed around, are you passing the sign-in sheet for presentations around? There's a, yeah. I'd like you to put down, if you don't know yet, you don't put it down if you don't know, but I'd like to know what your topic's going to be. If only by forcing you to write it down one of these days this week, it will, get you thinking. And I actually probably at the end of today give you some, if you don't have ideas, start giving some topics that I think could be topics if you haven't come up with one already. So let's get that blown up a little bit. So one of the things about stainless steels, I talked about active and passive and how they have better corrosion resistance. We talked about how regular carbon and alloy steels, their Achilles heel is their corrosion resistance. They've estimated that this country loses $200 billion a year to corrosion, and it's probably 80% of that cost is due to corrosion of steels, because steels are structural materials that we use most commonly. And even in concrete rebar, the rebar is steel and it corrodes, okay, in chloride environments so far as that goes. So in any case, you tend to use stainless steels in two types of environments. One is an aqueous system, where you need water corrosion resistance in some sort of water. Okay, aqueous. And the second one is high temperature oxidation. And these actually are, in one way they're similar, because it's the chrome oxide on the surface that forms the passive layer. In this case, there's no water around. You're above the melting temperature of water. But it is just still the stability of the chrome oxide on the surface that protects you from diffusing oxygen into the steel and forming a big thick layer of rust. Aqueous corrosion resistance, the Achilles heel there for stainless steels is chlorides. And we were talking about how you can add molybdenum, but at a price, something here that might be nowadays $4,000 a ton, maybe. I don't know if I said 2,000 or 4,000. Depends on what the current prices of chrome and nickel are. It's probably around 4,000 today. 10 years ago, it was probably 2,000. But 316 might add $10,000 a ton to that, and 317 might add $20,000 a ton to that. So you're getting pretty pricey. That gives you better chloride resistance. We haven't gotten up here to the nickel chrome iron alloys, where you add lots of nickel, and essentially you're 60% nickel, and these are $50,000 to $100,000 a ton. Okay, but that's sort of what you build nuclear reactors out of, these types of things. Although we build nuclear reactors out of this one, and when we do all kinds of things 304, because it's much cheaper, you don't want to build a nuclear reactor out of something that costs this much. Pressurized water reactors, they do make them out of this type of stuff. In any case, I started talking at the end about the low carbon versions of stainless steel and how the process for making low carbon stainless steel was essentially invented here at MIT, and that's the argon oxygen decarburization. What happens is, in a particular temperature range, which I'll show you in a little bit, you can precipitate chrome carbides at the grain boundaries. And because carbon will diffuse faster than chrome, when you precipitate the chrome carbides, you'll end up with a region that's depleted, or the carbon will come from lots of distances. You'll form lots of chrome carbides, and you'll end up with a low carbon region, a low chromium region. And so this might be 18% chrome right here, but in this region right here, it could be 10%. I've measured 8% chrome in some what we call sensitized stainless steels. Well, 8% chrome is not enough to be corrosion resistant. And in fact, this is just a plot of the cross-section. What's the cross-section shown in there? But anyway, you basically have dissolved metal. If you put this in a corrosive environment, you can eat away right around the carbide. The carbide doesn't dissolve, but the steel around it does because it's low chromium composition. And so if you weld these steels, actually this is a weld temperature plot, and you have some peak temperature, but you'll have some side temperature that's between 800 and 1,000 degrees roughly, and that will precipitate these chrome carbides. And if you take one of these stainless steels and put it in something like nitric acid, you'll end up with a region that will just dissolve away in the nitric acid, because nitric acid won't touch greater than 10 or 12% chromium stainless. But if I've got 8% stainless steel here, or 8% steel, it's just going to eat it away. It's called weld sensitization. It created a real problem for trying to weld stainless steels in the 1940s. People developed these other steels that had low carbon, but they had double and triple the price, until AOD came along, and now you can make it all that way. It's cheaper to just make everything, almost everything, low carbon. The precipitation of those chrome carbides, you don't have to worry about this unless you happen to be a metallurgist. If you look at temperature versus time, you can look at the precipitation kinetics, and you look here at different amounts of carbon. If you're down below, the specification for the L grade of stainless steel is 0.03 carbon or less. So that's 300 parts per million or less carbon. If you're down around 0.019 carbon, we can readily get that today. It'll take 100 hours of heating in that range to precipitate the chrome carbides because they're so little carbon to diffuse. But you're up here at 0.08, that's the specification for the maximum carbon in 304 steel. Not the 304L, but 304. Wow, it takes less than a minute. And so you can be welding stainless steels, and you could get the low chromium heat affected zone, which just be eaten away in a lot of acids. Yes?
So you're at like 800, you have 0.08.
Yep.
You go to like 1,000 hours, the precipitates dissolve.
No. This is just to start the reaction. The reaction, I've seen these plots where they show you the finishing, but this one they're trying to show you the carbon content. If you put the finishing reaction on top of this, everything would just look like a mess. Okay, so this is the reaction starting. If you go to 1,000 hours at that temperature, it's going to be down around 6%. Okay, chromium in that region. Okay, and so it'll just be even worse. Okay, so this is not that you don't have a problem, but what happens is if you go above 900 C, you can resolutionize those carbides, so you can heal the process. But above 900 C, the whole structural part could turn into a pretzel, okay, in the heat, in the annealing furnace, and you have to quench it through this region within less than a minute, and so it's not very practical. Okay, so you have to be careful how you heat treat stainless steels. Unless you're 304L, boy, you got 10 hours here. You can weld them all day long, but you can't operate them between 800 and 1,200 degrees, okay, Fahrenheit, or 500 and 700 degrees, okay. You can dissolve the chrome carbides at lower temperatures if you have lower carbon, okay. It's just, it's easier to dissolve it if there's less carbon in the matrix. Is this a problem? Yes. General Electric built nuclear reactors in the 1970s, and what happened to them, and they were surprised, they're using the world's cleanest water. You measure clean water if you were to take absolutely pure hydrogen, absolutely pure oxygen gas, and you can purify them very well, and react them to make water, and measure the electrical resistance of that water, it will be 18 megohms, okay? Whenever you put any mineral in there, some sulfate or chloride, the resistance goes down because the ions conduct electricity. So when we're talking about ultra pure water, we talk about nuclear reactor grade water, the goal is 18 megohms because that's the limit. That's absolutely pure water with no ions in it. It's distilled water. You don't even talk about resistance. It has lots of conductivity because there's still, even in distilled water, enough ions. But when you're getting down to parts per trillion or less of salt in the water, then you can start measuring the water purity in megohms. For example, I've got a failure of some stainless steel baskets that were filters in a not a nuclear reactor facility, but a coal-fired plant, or actually a gas-fired plant, I think, in Georgia. And they had 14 megohm water. 14 megohm water is pretty clean. Okay, it's very clean. And they said, oh, someone said, it's the chlorides in the water. There aren't a lot of chlorides in that water, okay, believe me. And I said, no, I don't think this is a corrosion problem. And it turns out it's not a corrosion problem, it's a design problem. It's a thermal problem for the way they designed what was going through this filter. But in any case, General Electric ran into this $2 billion worldwide problem because they had stress corrosion cracking in water that had 1/10 of a ppm chlorine and 1 ppm oxygen. And it's the combination of oxidizing chloride environment that kills stainless steels. No one in the world thought that you could get stress corrosion cracking in 304 stainless steel at those extremely low levels of oxygen and chlorine. And in fact, except in a nuclear reactor environment, okay, where you have high residual stresses and other things, you don't, okay, but they did. And it costs a fortune once the whole plant is radioactive to go in there and fix it, because people have to go in there in radioactive suits, and they can't stay in the radioactive environment very long before they get their yearly dose of radioactivity. And anyway, they fixed the problem, but they did a lot of things to improve the stainless steels such that now you can get 304L, was it L's? It's basically an ultra low carbon. It's like not much more than 0.01. But then when they got the carbon down that low, they didn't have enough tensile strength because carbon adds strength to steel. And so then they had to add nitrogen back. So 304LN is an extra low version of carbon that they put some nitrogen back. Nitrogen doesn't form the chrome carbides. Forms chrome nitrides, but they're not as stable. In any case, to get the strength back up. Okay, they did all kinds of other things. If you take that part of my welding course, I'll talk about it some more. But back in the 1940s and stuff, they created other grades, and they added titanium to the stainless steel. Rather than going to extra low carbon, the titanium would tie up the carbon as titanium carbide, and in fact that's what this picture is all about. It shows you two steels welded together. This one is regular old 304. This one is 321 stabilized with titanium. It's like 0.02% titanium, okay, to tie up the chrome carbide. And then they also came up with 347. They added niobium and tantalum, which are strong carbide formers, which does the same thing as titanium, okay? So all of this down here is basically ways to get around to the welding problems of chrome carbide precipitation. We call it sensitization. And it's a problem for aqueous corrosion resistance of stainless steel. Down here, there's a little aside. If you go to 317, which has lots of molybdenum, you can go to add even more molybdenum, up to 6% molybdenum. Now you're talking $60,000 a ton steel. Add more nickel, nitrogen, you get some higher strength, and you get what they call the super austenitic stainless steels. The U.S. Navy about 10 years ago was interested in building submarines out of this material. Why? because they're not magnetic. The problem with magnetic submarines is if you've got a superconducting quantum interference device up there on some satellite, you can see 100 feet down and you can see this long magnetic donut, or not donut, but hot dog in the ocean. Okay? But they finally gave up and said, our Navy has more ships than all the rest, more capital ships than all the rest of the world's navies combined. So, except the Chinese are starting to try to catch up with us. Sort of like what happened to Germany and France and Britain after World War I. So maybe we're heading for something else. Anyway, then they took the nickel out. This is another grade of stainless, and they formed 430, which is a ferritic stainless steel. And if you add some extra chrome and molybdenum, you can get a super ferritic. These have very good corrosion resistance, particularly in wet chloride environments and stuff, better than the austenitics so far as that goes. If you're adding chrome and nickel for strength and oxidation resistance, this is the second application of stainless steels. You want oxidation resistance at high temperatures. You go to things that are 30% chrome and 20% nickel, so it's only 50% iron. You're hard to call it a steel anymore. It's basically just a high alloy, and sometimes they call them heat-resisting materials rather than calling them steels, because you sort of get to the point where they're not steels. And if you get to the point where you get to the Inconel alloys, where you might be 60% nickel and only 20% iron, they aren't steels anymore. They're nickel-based alloys, but they all grew out of this 304. But now you're talking about alloys that can cost $30,000 to $100,000 a ton. Okay, not cheap. Now, we used to have steak fries in the department, and back in the early 1990s, I had some leftover Inconel sheet, leftover from some surplus, and I had four grills made out of this. I kind of designed them, and over in Building 13, we used to have steak fries on registration day when I was department head, and I used to call these my $30,000 griddles, okay, because the four of them weighed, I don't know, it was about 1,000 pounds, and if you think of Inconel sheet as back then about $30 a pound fabricated, if you'd gone out to purchase these, you would have probably had to pay $30,000 for them. I paid about $1,500 to have them fabricated, but the metal in them was great. They will last forever. Now, since then, Professor Suresh killed the steak fries. One of them got stolen. Another one I gave to the guy who used to run the forge. Another one I gave to a charitable organization. The last one's in my garage. Okay, but they were 2 feet by 4 feet, and you can cook a lot of steaks on a griddle that size. But anyway, so I made Inconel grills once upon a time, but that's another story. Any question? Oh, actually, I have some other stories on stainless steel. What are my other stories on stainless steel? I told you about the aquarium. Can't think of a stainless steel. Anybody have any questions on stainless steel? I had another one I was thinking of this morning, but that's okay. We might as well start on aluminum. So let's start on aluminum. Aluminum is the second most widely used metal in the world. And it's come a long way since 1850, when it was more valuable than gold. It's not the second most widely used structural material. The second most widely used structural material is concrete. Number 1 is stone. Number 2 is concrete. Number 3 is sort of steels. And number 4 would be kind of aluminum, so far as that goes. But in any case, it's second most widely used. It was more precious than gold. Now it's about 2.5 times, now it's about 5 times the price of steel on a weight basis, but on a volume basis, only about 2.5 times the price. So aluminum can substitute for steel when you need lightweight, particularly in something that like spacecraft or aircraft. And I'm going to show you an example of that and say, well, I might as well show it to you now. So everything I've told you about how wonderful steel is, now let me take it back and prove to you that it's not so valuable. If lightweight is important, that's another Achilles heel of steel. There is something, and I'm going to put this up. You might want to take a pen and pencil out if you have one and write this down, because you can get this for free. It's from the U.S. government. It used to be called Mill Handbook 5. It's a 9-volume set. If you want a hard copy, you have to pay $110 for all of this, okay? But it's the Metallic Materials Property Development and Standardization. It's now called MMPDS, which is all that stuff, -05. That's because for 40 years it was called Mill Handbook 5. This chapter 1, which is this thick, is an introduction to this. But if you read in the beginning, it tells it was historically grew out of Mill Handbook 5. You don't have to read all this stuff. But in spring of 2004, it was classified as a non-current, anyway, Mill Handbook 5. But anyway, they switched it to this. But this is a joint publication by the Federal Aviation Administration and the Department of Defense. And if you want to build an aircraft or a spacecraft, this has the properties for a whole wide range of aerospace materials, and you must meet this as the minimum standard. If you want to have a higher standard for your material, you can, but your material must meet these qualities. Okay? It actually has several different qualities in here, one for spacecraft and one for aircraft. And it has statistics in here. This has been built up over 50 years. There are guidelines, which of course the guidelines are thicker than the introduction. But what I really wanted to show you, here's the volume on steel. Here are the 3 volumes on aluminum. So which one's more important than steel? Duh, aluminum happens to be more important than steel in aerospace applications. Okay? What's in these things? Oh, it's exciting reading, believe me. But you can get it for free. All you have to do is log on and download it. All of these in digital, it will give you, this happens to be, well, this is castings. This is 2000. Now they only go through 2000 through 5000 series. I haven't told you what this series of aluminum alloys are, but it will give you for the A and B grade. I have to look in the thing. Pardon me? I turned it off? Oh, good. Okay, let's see if I can turn it back on. What did I turn off? There you go. So if I come in here, here's a table, and there's the A and B grade. One of them's aerospace and one of them's aircraft. Aerospace might be something they require for some military jet as opposed to some commercial jet. It's got the mechanical properties, longitudinal, transverse, okay? For this particular material is clad 2014 aluminum sheet and plate, which is what the outside surface of old Boeing aircraft or McDonnell Douglas aircraft used to be made out of. And it will go on for about 20 pages. It will give you graphs of the minimum properties. These are the design properties. If you're going to design an aircraft for military or civilian applications and you want to get government certification, you must certify that everything you put in your aircraft meets these minimum standards. You can have higher standards, but these are the minimum. And it's built up after 50 years. And some of it's data from Boeing, McDonnell Douglas, government laboratories, all kinds of places. And just goes on and on so far as that goes. Now they have 9 volumes. And they have titles such as, I showed you steels. Chapter 4 is magnesium alloys, not very thick. I'll talk about magnesium later and why we don't use it very much. Chapter 5 is titanium alloys, obviously used a lot and almost as thick as steels because we use more titanium than steels in aircraft. Heat resistant alloys. This is sort of what might go in your jet engine, okay? So, hey, you're building a nuclear reactor, you want to know the properties of heat-resistant alloys, this is a good place to start, okay? Miscellaneous alloys and hybrid materials, not very thick. It's got some resin composites and cherry lock fashion. Anyway, it's got fasteners. It's got, anyway, lots of different things, but it's not very thick. And then the last thing you want in an aircraft is joints, and so they have a fairly thick thing on structural joints that tell you what the strength capabilities, mostly of aluminum alloys, when you start to weld them, because a lot of your high-strength aluminum alloys lose their strength. And it also has data on rivets, riveted joints and things. So that's a free resource. Just download it if you want a hard copy like me, because you don't know how to use a computer. Actually, I have a copy of both. And I was thinking this morning, there are some other really good government handbooks that are free that I start telling you about that you can download. Just starting a library of free resources from the government. Now, aluminum is also great because it's relatively low melting, okay? And that means like 660 degrees centigrade as opposed to 1500 for steel centigrade, or titanium is 1600 centigrade. Nickel alloys are 1400 centigrade. In any case, aluminum is much lower melting, and therefore you can extrude it, you can make fancy shapes, you can do all kinds of things with it that you can't do with steel. So aluminum's great in that sense. Aluminum, here's where the market for aluminum is. A number of key things. Beverage containers is the largest single use for aluminum. I saved one of my sodas the other day. Okay, aluminum cans. That is 30 to 40% of the aluminum market. This has got exports, because exports don't really count for a product. It's actually just shipping aluminum overseas. But containers and packaging, that could also include aluminum foil in there. Transportation, which is all your aerospace, but also includes railroad cars. A lot of railroad cars are made out of aluminum because it's lightweight. Every pound, you know, they have limits of weight on the railroad, just like they have limits of weight on the highway. More and more, we're using aluminum in heavy trucks. I remember as an assistant professor, Professor Fleming's arranged for, well, actually, one of his classmates, whose last name was Walther, who had graduated from MIT in the early 50s with Professor Fleming's, needed some welding help because they were trying to weld aluminum tire rims. And it turns out Dayton Walther Corporation was the world's largest manufacturer of tire rims at the time. And they, at that time, in the late 70s, everything was steel rims, because the aluminum rims couldn't meet the 500,000 or million mile fatigue limits that you had to have for truck wheels. Cars, yeah, we had aluminum wheels on cars because they only went 100,000 miles before the steel rusted out and it was a piece of junk, okay? But trucks, they get a lot of miles on them. And so I went out to Dayton Walther and met with him, and they were trying to basically put aluminum in the rims of truck wheels. We now do that. Alcoa, you go to the Cleveland plant and they forge these great big, they don't weld, good reason to stay away from welding. They forge aluminum rims, and they're getting the weight out, and it saves, you know, I don't know how many thousands of gallons of diesel fuel over the life of the vehicle. And they get 1 million miles on these things. Building and construction, you know, you have aluminum frame windows, you have aluminum siding, you have lots of things. Electrical, aluminum is second to copper in large volume electrical conductors, okay? There are better electrical conductors. Silver, for example, is better than copper, but it's a little pricey. Consumer durables, so you got some Wii or computer or something, it's got, anyway. whatever that is, machinery and equipment. So that's where aluminum is used. Lots of different markets, but the big one is beverage containers. And by the way, well, that's another story, but I mentioned briefly, these things are getting thinner and thinner over time. And they're different pressures. Soda cans have to have a little more pressure than beer cans because they develop higher pressures. There are actually 3 different aluminum alloys in here, which leads me to aluminum alloys. The aluminum alloy system for the Aluminum Association is there are, oops, a little too much, 1000 series aluminum. If you have aluminum 1000 alloy, it's 99% aluminum, essentially pure aluminum. I think 1060 alloy is 99.6% aluminum or something like that, or 99.4, I can't remember. You can get up to 4 nines aluminum commercially. Problem is these 1000 series alloys, they don't have strengths better than about 6 or 8 KSI. So if you look at this mill handbook, the old mill handbook here, it has the 2000 series alloys to the 5000 series alloys, and then it has the 6000 to 7000 series alloys. It doesn't have the 1000 series alloys because no one's going to make an aircraft out of something that's only got 6,000 to 8,000 KSI strength. It's going to be too heavy for the loads that are imposed on it. Copper-based, that was the original heat-treatable aluminum alloys. The Wright brothers engine block on the Kitty Hawk, or not Kitty Hawk, that's where they flew it. What was the name of their aircraft? I can't remember. Pardon me? Yeah, Flyer 1 or something, yeah. But the one they flew at Kitty Hawk, Flyer 1, it was an aluminum copper alloy. That engine block is in the Smithsonian. A few years ago, they went and they looked at, they took a little piece out of it and they looked at it in the transmission electron microscope to see how big the aluminum copper precipitates were after 100 years since they've been heat treated. And they put that, they're coarsening over time. One of the problems with aluminum alloys, they melt at low temperatures, but they will also soften. You can heat treat them, and you can get 10, 12 times the strength of pure aluminum, but they can degrade over time at relatively low temperatures. I think, did I tell you the story that the SST, the Concorde that the French and British built, flew not on speed, but on temperature? The skin temperature was limiting their speed. They had sensors to measure the temperature of the outside skin. So if you're up there and it's really cold out, you could go faster. I mean, it could go faster. I flew the Concorde once. I didn't tell you this story. This was back in the 90s, and I'd never flown a supersonic transport. Most people hadn't. So I had to go over to Europe for something, and MIT had to pay my business class airfare. And I said, okay, I will spend the $2,400 for the upgrade coming back out of my own pocket just to see what it's like to fly on an SST. Well, it was an interesting experience, to say the least. First thing is you do not get jet lag when you fly on an SST. The only thing I can figure is the flight is shortened so much. I mean, we took off from London at 5 o'clock. London time, we arrived in New York at Kennedy at 4:45 New York time, 15 minutes earlier, okay? Of course, a few time zones in between. But anyway, it's a relatively short flight. And I noticed the next day at 4 o'clock, I'm working in the garden, and I realized I don't have jet lag. You don't get jet lag. That's true. You're flying super first class. Everybody who has a ticket is in super first class, and everybody wants to board at the first. Okay. It also is a very small cockpit, or not cockpit, but fuselage, and so it's sort of like being on a small commuter jet in terms of the size of the seats. They also had limited aircraft, and so they never had time to do maintenance. It was the filthiest commercial airplane I've ever been on. The food was terrible. The maintenance was terrible. The guy I was sitting next to was the #1 flyer on British Airways, and they saved his ticket. I was in seat 1B because I had made my reservation 6 weeks before. Most people who would fly with the Concorde were these super wealthy people who would make their reservations a couple of days ahead of time. They saved 1A for this guy. every Friday afternoon until noon. And if he called before noon on Friday, he would get that seat. Because he was 23 years old. His father was a Greek shipping tycoon. And his typical week was to fly around the world. Okay? He would decide whether he was going to go from London to New York on a Friday and work Saturday and Sunday morning in the New York City office, and then he would get the 2 o'clock flight back from JFK to London on Sunday, and then he told me his itinerary, and he was going on Monday morning, he was flying to somewhere in the Middle East, and then somewhere in India, and then somewhere in Japan or whatever. And he would go around the world once a week, which is why he had the most frequent flyer miles. But his tray table was broken. He had to eat while holding one hand, holding the table in the other hand. He could only eat one-handed because the tray table was broken. They didn't have time to maintain the equipment, okay? Which gives you a lot of confidence as you're flying, to know that your aircraft they didn't have time to maintain it. But in any case, aluminum, what did I want to say about aluminum? Oh, well, I can talk about aluminum lithium alloys are actually, I was going to talk about some of the other alloys designations. So the other alloy designations here, copper, 3000 series are manganese. They're basically like the 1000 series, but they have about 1% manganese and gives them some strength. So the can stock, the body of the can, is typically 3003 or 3004 alloy. The top, I think, is a 5000 series alloy because they have to stamp it. It has to have a certain strength. And the pull tab is a third alloy. And recycling these gets to be a little bit of a problem because you've got aluminum manganese alloys, aluminum magnesium alloys, and then I think the other one is also 5000 series. But if you mix them all together and melt them all at once, you got a problem because you don't want manganese in your 5000 series. What are you going to use this for? And you're recycling. This is 40% of your recycling stream, maybe more. So that creates a little bit of problem, but people chop the cans up into little pieces and try to separate and things like that, but there are different things you can do. Magnesium silicon, 6000 series alloy, 6061 is a workhorse alloy. You want an aluminum structure and you want to order it from some local place, you can get anything you want in 6061 T6. It's the workhorse heat treatable alloy. The 7000 series, which are zinc based, are the ones they used to use for aircraft for the first 50 years. Now they tend to use some of the 8000 series alloys, which is special alloys, okay, other elements, and 9000 series is unused. Well, the other elements are basically things like aluminum lithium. And if you look at aluminum lithium was a big deal when I was an assistant professor, yeah. No, because of corrosion resistance, stress corrosion cracking. And they've come up with 7079 sort of started to replace 7075. If I started looking through, there's another one, 7175, I think it is. I can't remember the designations. But if you were circa 1960, 7075 and 2024 were the two workhorse alloys. In the 70s, they started getting better fatigue resistance. Lots of fatigue data. More fatigue data on aluminum than on steels. Okay, there's actually a reason for that I'm not going to go into. But one of the reasons is we use them for aircraft, and aircraft are nothing more than flying fatigue machines. They vibrate, and they tend to be life limiting. If I look at, sun's coming out. Wait a second. If I look at a commercial jet, and this was out of I think a 1998 book. So this was probably, doesn't say it, but it might have been a 77, what they ended up using in a 777. The aluminum lithium alloys were sort of developed in the former Soviet Union, and they have like 5 to 10% lithium in them. Lithium is very light, and that gives you a lower density. okay, a 10% lower density, but it also increases the modulus, which is sort of interesting. Usually alloying doesn't change, at that level doesn't change the modulus of the material, but it actually increases the modulus by 10 or 15%. And if you look at structural beams in bending, the modulus divided by the density, E over rho, is the relevant parameter, okay? And if you get 10 or 15% higher modulus and 10% lower density, you all of a sudden get a 20-25% improvement in stiffness of your alloy. You can eliminate 25% of your weight. So all through the 1980s, late 70s, early 80s, huge amount of research on aluminum lithium alloys. The military started using them in the mid 80s. Commercially started using them in the 90s. And there are all kinds of alloys, 80, 90, T81. The T is a heat treatment and temper to the aluminum. But any of the 8000 series that you would see on this little plot, this comes out of this book on material selection and design. You look at this is probably this is a concept vehicle probably for what's now the F-22 or Joint Strike Fighter or something early on, using 80-90 where they can. A lot of these skins and stuff end up being titanium because of the supersonic speeds and the temperatures. You need something that's much better. So the aluminum and lithium alloys give you some tremendous strength. Actually, I should have left this one up, or maybe I didn't even put it up. These are some of the aluminum and lithium alloy properties. And if you look at the alloys and you look at tensile strengths, you can get 90,000, 94,000 tensile strength KSI. The yield strength would be 88, 60 to 88 in these aluminum lithium alloys. And in the 7000 series, you can get those types of strengths too, but you don't have the good E over rho that you get from aluminum lithium. So what's supplanted the 7000 series in 70-75, it was better 7000 series, and now it's better 8000 series, mostly because of it's just this aluminum lithium E over rho. But they had to develop forming, and first they had to develop casting techniques so they could get homogeneous melts, ingots, and then they had to worry about forming, they had to worry about joining. It takes 20 years to bring one of these things on and get it qualified. And I don't even think this 2010 edition of the Mill Handbook really has the 8000 series in there. You probably have to certify to the FAA, this is what we got, and eventually it will probably find its way in. But it takes time to get into codes and standards. So the aluminum lithium alloys have up to 95 KSI strength, but your homework problem was what product uses the highest strength aluminum alloys? And I told you it wasn't Aerospace. Anybody figure it out? Well, if you look here, you'll find it. It's right here. 100 KSI. I have a baseball here somewhere. Anyway, where'd my baseball go? Oh well. Oh, it's in the bin? I thought it was in the bin. Yeah, okay. It's under my... Okay, so this is about the right time to just tell you the story. But if I put this up, I paid $130 on Amazon for this. Typically, you might pay $300 for a bat. This has got, it's a THT 100 alloy, scandium alloy. This is the world's largest use for scandium. We only make 2 tons of scandium a year. And the Soviets discovered this, again, that scandium is a tremendous grain refiner. When they make these metal bats, they extrude them, and they have a relatively thin wall. This may have a 28 thousandths or so wall. Well, it has 100 KSI strength. And when you hit it with the ball, it will go farther than with a wooden bat. It's lighter than a wooden bat. It has to weigh a certain amount. This is a -10 bat. See the -10? That means it's 29 inches long and it weighs 19 ounces. You take 19 ounces and subtract 29 inches, and you get minus 10. They were making a few years ago minus 13 bats, but they would almost crack the first time you hit a ball with them. Okay, and they're great business because you can sell anything to a sports fan. Okay, and the best sports fan, I talked to some of you a while ago, are golfers, because they're past middle age, they've got disposable income. You can sell anything to a golfer. If he thinks it'll allow him to snub his business acquaintance at the 19th hole, he will pay for it, okay, and pay a lot for it, out of all kinds of materials. But they basically extrude a tube, and after they extrude the tube, they put it in what we call a swaging machine, which is rotary hammers that basically thicken up this region. But there's a lot of technology goes into this. Most of it comes out of Southern California because a lot of people who worked on this were the aerospace engineers who used to work on the high-strength alloys for the aircraft. But as they're extruding it, they control the extrusion ratio so that it comes out at the temperature where it's solutionized, and they quench it as it's shooting out of the extrusion machine. And it's got scandium as a grain refiner, which is better than titanium or zirconium or the other things we typically use on the bigger alloys. And you can get extremely fine grain, extremely high strength that will hopefully last long enough that you won't get too upset. If you go on the web and find people's comments about the bats, broke the first time we hit it, dented the first time we hit it because it's so thin. Others will say, well, this lasted for a while. The product insert that came with it the other day basically said on the little warranty, okay, card, rotate bat 1/4 turn each at bat. Okay, because you don't have to worry about hitting it with the grain. You got to worry about distributing the dents, okay, or not building up residual stress. I don't know. I haven't studied that in detail, but I did study bats and injuries for another application, and that was a kid was playing Little League down in New Jersey, and it was a minus 12 bat that Little League approved, and the pitcher got hit in the chest and his heart stopped, and now he's on a ventilator for the rest of his life. And there have been people who've died. This was a little worse because it's easier to die when you're 16 years old or 14 years old than to live the rest of your life on a ventilator, although most of those people on ventilators don't live that long. But in any case, I was asked actually several times if I would take an aluminum bat case, because most people didn't want to take the aluminum bat cases. So I tried to pass them on to Professor Lagasse over in Aero and Astro. He's a big Red Sox fan. I mean, he's a consultant to the Red Sox. He did a model of Fenway Park and put it in the MIT wind tunnel to show that when they put the press boxes up there, they actually did hit more home runs because of the change in the wind pattern coming over the press boxes. Okay? So Paul is a baseball nut. And I tried to pass him on to Paul, and Paul thought about doing it for a while, and he decided that he didn't want to. They finally came back to me and said, well, won't you do it for us? And I said, yeah, I'll look at it. And so they finally called me up. This was a few years ago. It was like the Friday afternoon before, it wasn't Thanksgiving, but it was right around there. And they said, we need you to, you said you'd do this. I said, yeah. But they hadn't sent me anything. So I didn't know anything about the whole problem. And they said, we need the report by next Thursday. So they gave me like less than 1 week. The problem is, I was leaving on Monday for a trip. And I said, you realize I have to write this tonight, okay? And so I went home that Friday night, and I said, what am I going to write? I don't have any data. They sent me one report that time, that some people had done some high-speed movies at the Naval Surface Weapons Lab in China Lake, California, of a ball hitting a bat, okay? So I looked at the high-speed movie, and it showed the dent in the bat on impact and the dent in the ball on impact. And I thought, well, I learned in freshman physics, even though I almost flunked it, okay? I did learn something. I learned that the maximum momentum energy transfer is, when do you get the maximum momentum and energy transfer? When the two parts weigh the same, okay? If I'd ordered some ping pong balls to show you the coefficient of restitution, but I can drop the bat on a sort of hard surface and it bounces up 20-30%. It doesn't have very good coefficient of restitution. If it bounced up 100%, it would be all elastic. It would be 100% elastic energy, loses no plastic, no energy losses. If I took a beanbag and dropped it, it goes splat and there's no bounce to the beanbag. 100% plastic, okay? And coefficient of restitution is just the ratio between 0, 100% energy loss, and 1, 100% elastic rebound. But if you go through, and I didn't have my old physics book, probably don't sell it anymore after I burned it. But in any case, if you go through, I had Feynman, and I already turned this off, but here's a section on momentum and energy conservation. You write down 1/2 mv squared conservation of energy equation. You write down mv, conservation of momentum equation. You solve those two equations simultaneously. This was a homework problem I never could figure out, okay, as a freshman. But I did remember, because I did so poorly on it. And he has something in here where he describes conservation of momentum and energy. And so I went up and I wrote about 3 or 4 pages about the fundamental principles are that you want the same stiffness. I changed momentum and energy to elastic stiffness like springs. It's the same formulas. 1/2 kx squared, and the force is minus kx, okay, or kx or whatever. Anyway, I wrote it all in words about how you want to match the stiffness of the ball to the stiffness of the bat. And from this high-speed video photograph I saw, they had matched the they were, by going to 28 thousandths thick, they were close to matching the stiffness of the bat to the stiffness of the ball. And I wrote this report. The next week I actually got some balls and actually put them in a compression machine and measured its relative stiffness. Has a lot of hysteresis, which complicates things. But nonetheless, and we already had, I think we may have taken an exemplar bat and we pushed onto the bat and we measured its stiffness, and lo and behold, they were the same within like 30 or 40%, okay? So billiard balls are great. Equal mass objects, you can prove, have the best combination of transfer of momentum and energy from one object to the next. So you wanted equal stiffness. And so I started looking. Eventually I got 10,000 pages or 50,000 pages, I think, of discovery of all the tests they'd done on these things. And sure enough, they make them for maximum performance. And in fact, it says right here on the little insert, this is a high-performance product designed to deliver maximum performance within the limits of the association rules. Okay? Many of the associations, the Japanese kind of started in their colleges, and they said, you can't have more than, I think, a -8 bat in Japan in college. US NCAA has been talking about things Little League never did. They said, our kids aren't strong enough to do anything. But people, I think they may have gotten to the point now where -10 is about the most anybody can make. But they're still going to the best aluminum alloys. You get on the web and it will give you the history of the last 30 years of how Alcoa is developing the highest strength aluminum alloys for bats. Not for aircraft, but for bats. Because let's face it, 19 ounces, 130 bucks. That's $100 a pound, folks. Someone's making a profit off this. Pretty good markup. Anyway, okay, so now you know what the highest tech aluminum product is.
Do the cartridges